Hello students, in this video I will discuss ionic or electrovalent bond and some bond parameters. Let us start with ionic or electrovalent bond. As we know that ionic bond is found in between two ions of opposite charges, that is cation and anion. In the formation of a positive ion involves ionization, that is removal of electron, and during formation of anion, an electron is added to the neutral atom. During formation of cation, some amount of energy is supplied to the atom, which is known as ionization enthalpy, and during formation of anion, some amount of energy is released, which is known as electron gain enthalpy. These cation and anions now attached with each other through electrostatic force of attraction, an ionic compound is formed. Now the stability of this ionic compound depends upon some of these energies, that is ionization enthalpy, electron gain enthalpy, and energy released during formation of ionic compound. Ionic compounds in the crystalline state consist of orderly three-dimensional arrangement of cations and anions held together by Coulombic interaction energies. As shown in this diagram, it is a crystal of sodium chloride in which each sodium ion is surrounded by chloride ions and chloride ions are surrounded by sodium ions. In ionic solids, the sum of electron gain enthalpy and the ionization enthalpy may be positive. Positive means it is not a favorable condition for formation of ionic compound, as positive sign indicates that it is an endothermic process. But still the crystal structure gets stabilized due to the energy released in the formation of crystal lattice. Okay. For example, sum of ionization enthalpy and electron gain enthalpy for sodium ion and chloride ion is plus 147.1 kJ per mole. This positive sign indicates that sodium chloride compound cannot be formed, but its lattice energy is minus 788 kJ per mole. Therefore, the energy released in this case is more than the energy absorbed. That means this process is exothermic and hence sodium chloride crystal can be formed. Thus, a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in gaseous state. That means formation of ionic crystal doesn't depend upon ease of formation of cation or anion, but also it depends upon value of enthalpy of lattice. So let us discuss about lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. For example, the lattice enthalpy of sodium chloride is 788 kJ per mole. This means that 788 kJ of energy is required to separate 1 mole of solid NaCl into 1 mole of sodium ion and 1 mole of chloride ion in gaseous state to an infinite distance. Okay. Now this process involves attractive forces between ions of opposite charges, and also it involves repulsive forces between ions of same charge. Now it also depends upon various factors. Let us discuss these various factors one by one. These factors are broadly categorized as bond parameters. First is bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Okay. So each atom of a bonded pair contributes to the bond length. In the case of a covalent bond, the contribution from each atom is called the covalent radius of that atom, and this is shown in this diagram. Here A and B atoms are covalently bonded with each other. Now half of the distance between their nucleus is called as covalent radius. Now another radius is more important, which is called as van der Waals radius. The van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. The van der Waals radius is half of the distance between two similar atoms. Okay? It is the half of the distance between two similar atoms in a separate molecule in a solid. Okay? It is shown here. This is covalent radius and this is van der Waals radius. So, lattice enthalpy depends upon bond length also. More is the bond length, lesser is the bond enthalpy or lattice enthalpy. Now next parameter is bond angle. Bond angle, as name implies, it is the angle between two bonds in a molecule. It can be shown for water molecules. Here oxygen is the central atom. So around this oxygen, the angle between two OH bonds is known as bond angle, and it can be defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. It is expressed in degrees and it can be experimentally determined by spectroscopic methods. Next is bond enthalpy. It is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. For example, the HH bond enthalpy in hydrogen molecule is 435.8 kilojoule per mole, and it can be depicted by this equation. Similarly, bond enthalpy for molecules containing multiple bonds can also be calculated. Bond enthalpy and strength of bond are proportional to each other. That means we can say that if bond is strong, then its bond enthalpy is also high. In case of polyatomic molecules, the bond strength is measured in terms of average bond enthalpy. It is the average of bond enthalpy of each bond present in the molecule. As each bond enthalpy is different from other one, so average bond enthalpy is taken for polyatomic molecules. Next is bond order. In the Lewis description of covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. So, if single bond is there in between two atoms, then bond order is 1. In case of double bond, bond order is 2. And if triple bond is present in between two atoms, then its bond order is said to be 3. Isoelectronic molecules and ions have identical bond orders. For example, F2 and O2 minus. These are isoelectronic species. These have bond order 1, N2, CO, NO plus. These are also isoelectronic and these have bond order 3. A general correlation is useful for understanding the stabilities of molecules, in that with increase in bond order, bond enthalpy increases and bond length decreases. So we can say that more is the bond order, more is bond enthalpy, and lesser is bond length. Next topic is resonance structure. It is often observed that a single Lewis structure is inadequate for the representation of a molecule, and this structure cannot explain all the properties of molecules. For example, ozone molecule can be represented by these two structures. An actual structure of ozone molecule is this. These two structures, structure number 1 and structure number 2, are known as its canonical structures, as these two contribute towards third structure, which is known as hybrid structure or resonance hybrid of structure 1 and structure 2. As ozone molecule is represented by structure 1 and structure 2 also, so this process is known as resonance, and these two structures are known as resonating structures. In both structures, we have a OO single bond and OO double bond. Okay, OO single bond here, OO double bond here, also double bond and single bond. Okay, the normal O single bond O and O double bond O bond length are 148 picometer and 121 picometer respectively. Now experimentally, it was determined that oxygen-oxygen bond length in ozone molecule are same, which is equals to 128 picometer. Means this value is in between value of single bond 148 picometer and value of double bond 121 picometer. Thus the oxygen-oxygen bond in the O3 molecule are intermediate between the double and a single bond, and this cannot be represented by either of the two Lewis structures as shown by structure 1 and 2. So the concept of resonance was introduced to deal with the type of difficulty, as we have discussed for ozone molecule. So according to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pair of electrons are taken as the canonical structure of the hybrid, which describes the molecule accurately. Okay. So resonance hybrid is associated with least energy, and hence it is said to be most stable structure, and canonical structures are associated with high energy. So canonical structures are not stable, whereas hybrid structure is a stable one. So in general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure, and resonance average the bond characteristics as a whole. Thus the energy of ozone molecule, that is O3 resonance hybrid, is lower than either of the two canonical structures, as we have seen structure 1 and structure 2. Now next topic is polarity of bonds. When covalent bond is formed between two similar atoms, for example H2O2 Cl2, the shared pair of electron is equally attracted by the two atoms. When covalent bond is formed in between two similar atoms, then shared electron pair is attracted by two atoms equally, as their electronegativities are same. But if this bond is formed in between two different atoms, then electronegativity of atom decides whether electrons are equally distributed between these two atoms or equally attached by these two atoms or not. For example, molecule of hydrogen fluoride HF. This molecule is formed by the sharing of 1 electron by hydrogen and fluorine atom. Since we know that electronegativity of fluorine is more than the electronegativity of hydrogen, so in this way this shared electron pair is attracted by fluorine atoms strongly as compared to hydrogen, and in this way this fluorine acquires partially negative charge and hydrogen acquires partially positive charge. That means this covalent bond has some polar character, and due to this polar character this molecule has some dipole moment. Dipole moment is the value that describes the polarity of a bond, Its Greek letter is mu, and it is expressed as dipole moment mu is equals to charge q into distance of separation of atoms, that is r. Dipole moment is usually expressed in debye units d. The conversion factor of debye to Coulomb meter is this. Dipole moment is a vector quantity. Okay, it is represented by this symbol. Fluorine is more electronegative as compared to hydrogen, so arrow is drawn towards fluorine and a cross sign at the side of hydrogen. So this is the way by which we can represent polarity in a bond or distribution of electron or electron displacement towards an atom with more electronegativity. In case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of bonds known as bond dipoles, but also on the spatial arrangement of various bonds in the molecule. So dipole moment of a molecule, when our molecule is polyatomic, then it depends upon two factors, that is bond dipole and the spatial arrangement of various bonds in the molecule. In such case, the dipole moment of a molecule is the vector sum of the dipole moment of various bonds. For example, in H2O molecule, which has a bent structure, the two OH bonds are oriented at an angle of 104.5 degree. Net dipole moment of 6.17 into 10 to the power minus 30 Coulomb meter is the resultant of dipole moment of two OH bonds, and it can be represented by this diagram A and B. The dipole moment in case of beryllium fluoride BeF2 is 0. This is because the two equal bond dipoles point in opposite direction and cancel the effect of each other. Okay. In tetraatomic molecules, for example, in BF3, the dipole moment is 0, although the Ba bonds are oriented at an angle of 120 degree. Okay. The three bond moments give net sum of 0 as the resultant of any two is equal and opposite to the third. The sum of bond dipoles of 2 is equal and opposite to third one. So net dipole moment is 0 for BF3 molecule. Now in case of NH3 and NF3, although fluorine is more electronegative means we can assume that dipole moment of NF3 will be more as compared to NH3, but actually dipole moment of NH3 is more than NF3. Let us discuss why it is so. In case of NH3, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of NH bond, that is direction is same. Whereas in NF3, the orbital dipole is in the direction of opposite to the resultant dipole moment of 3 NF bonds. These are in this direction and orbital dipole is in this direction. So these two are opposite to each other and hence dipole moment of NF3 is lesser than dipole moment of NH3. So just as all the covalent bonds have some partial ionic character, the ionic bonds also have partial covalent character. The partial covalent character of ionic bonds was discussed by Fazens. Now the rules for covalent character in ionic bond are: first rule, the smaller the size of cation and the larger the size of the anion, the greater the covalent character of an ionic bond. Smaller is cation, larger is anion. Okay, so there is a covalent character in this ionic bond. Next is, the greater the charge on the cation, the greater the covalent character of the ionic bond. If the size and charge of two cations are same, then polarizing power depends upon their electronic configuration. The cation with noble gas configuration is less polarizing in nature as compared to other cation. The cation polarizes the anion, that means cation pulls electron cloud of anion towards itself. So if cation is very small in size and anion is very large in size, then polarizing power of cation is more and polarizability of anion is more, and in this way this ionic bond acquires covalent character because cation pulls these electrons and hence it has a force of attraction on its electron, that is the electron of anion, and in this way a covalent character appears in ionic bond. So this is all about this video. In next video I will discuss some theories which can explain shape of molecules. Thank you.